Hi again, I am Elif. In this video, before giving the solution of exercise 2, I want to explain what a joint of an endomorphism means by simply following section 4.3. So in this section, first we need to be careful that we are working on vector spaces over real numbers, and this vector space is endowed with a scalar product, so that means it is positive, definite, and symmetric bilinear form. And we say that an endomorphism U has an adjoint if there exists V. In the lecture note it is denoted by U star, but I will denote it by V, such that for all vectors in the vector space we have this equality with respect to the scalar product. So this equality means, in some sense, gives us a correspondence between the left application and the right application. But of course, whenever we have U, when we have this right application, and what is the V which gives this equality. So for instance, a toy example can be considered in the vector space R square, and the standard with the standard inner product, and an endomorphism can be defined by matrices, and we can see that adjoint of A is the A transpose. But in this example, we have a vector space of continuous functions over real numbers. They are spatial kind of continuous functions because they are polynomials. So whenever we see a vector space, first we need to decide if it is finite dimensional or infinite dimensional, or correspondingly a basis. So for this example, we may consider this basis. And obviously, this is infinite dimensional. And we also want to see that the given bilinear form is a scalar product. So that means it's obviously positive, symmetric, and to see that it is also definite, we use a fact from the analysis which say that whenever we have a positive, f square is always positive, and continuous function on the interval, in the closed interval 0 and 1, this implies that f square t is going to be 0, and we may conclude that this polynomial will be 0 in this interval. So that means it's going to be vanished for infinitely many real numbers. So that means it is identically 0 for all t in R. So this gives us, this form is definite. And we want to decide this given U, this is obviously linear. Actually, this is functional, but you may consider the constant polynomials. as real numbers in this vector space. And now we want to decide U has an adjoint. So that means we want to decide if there exists V such that for all F and G in E, we have this equality. By the way, here note that I denote this bilinear form as denoted by as a parenthesis. So that means we want to see this equality with respect to this bilinear form. And I mean, here note that since E is not finite dimensional, we can't simply apply theorem 4.4 because, as it is mentioned in the remark 4.5, the proof doesn't work. In fact, example 2 is a counterexample for this remark. So see remark 4.5. So for this, I mean, to see that it's the counterexample, we are going to work with, we want to see that we have this equality for all F and G, but let me observe what happens if we consider the basis, if we work with the basis to see this equality. So that means if we have, we suppose that we have an adjoint and we obtain a contradiction. And to see this contradiction, again, similarly, we suppose that we have this is F, this is G, this equality. Actually, we suppose that there exists V, which gives us for all N, which gives us this equality. Okay, so we make literally computation. So the left hand side, we both consider the definition of the bilist scalar product and the definition of U. This is T to the N square root of T, dt, and ds, which is equal to 1 over n plus 1 over 2, because you can write it T to the n minus 1 over 2 and take the integral and plug in the boundary values and so on. And for the right hand side, first we don't know the form of V, right? But we know that V is also endomorphism. So we have basis elements on the left hand side. So Vf0, the image, should be also the linear combination of the fj's, right? So that means it can be written as a linear combination of fj's. These are t to the j's. And here note that this m and the coefficients only depending on the f0. So if you evaluate f1 and fn, they are going to change. And by this observation, we again use the definition of the bilinear form and the image of Vf0 under V. And when we compute this integration, I want to write one more step. alpha j t to the n plus j dt. And this is going to be the sum of alpha j over j plus n plus 1. So, okay, we want to see that we have this equality for all n, right? So, actually we need, okay, we in this case we are only considering the natural numbers, but to obtain the contradiction we need to extend our solution for the real numbers. So for this purpose we will interpret this function depending on n as z by setting z as n. And for this, again, the same interpretation. We now see these terms as functionals. And in fact, we want to see that this R of z, let me define R of z as a difference of these two rational functionals. And let me write it explicitly, this sum. Okay, so by setting denominators equal, we will see that as a division of two polynomials in variable z. And again, after setting the denominators equal, we see that actually the denominator is equal to this polynomial. And for all positive numbers, like natural numbers, this is always strictly bigger than 0. So, but we want to see that this rational function is 0. That means p of z is 0. So if this polynomial p of z is 0 for all natural numbers, so that means it has infinite many roots, it is contradiction, it should be identical to 0. And if it is identical to 0, that means for all actually real numbers, since pz is 0, rz is going to be 0. So that means we need to see this equality for all real numbers. But for the particular real number minus 1 over 2, if we consider what happens for the values in this neighborhood, and by approaching minus 1 over 2 from the right hand side, this is limit of the left hand side, gives us infinity. But the right hand side, the limit of the right hand side, is going to be a real number which is expressed as a finite sum of the series. So this is not equal. So that means U doesn't have an adjoint, and this shows us, this nice example shows us actually there's no frontier between algebra and analysis, so many. And yeah, thanks for your attention. See you in the next video. Bye bye.